Hello everyone, we were from Zhongshan Medical University, and today we'll be talking about our project Decolorgy. So it all started with a coincidence. Taiwan used to be one of the rainiest countries in the world, but something unusual happened in the back from last year. It started to rain less, causing to another big issue, water scarcity. Even though Taiwan now is facing water shortage, but the textile factory still dump tons of wastewater into the riverbank, polluting our environment. And this isn't just a single case. We then came up with an idea. Maybe we can combine two of the issues and tackle it all at once. So then we do more research into the issue and found out that textile production uses around 93 billion cubic meters of water annually due to the fast-growing fashion industry. And this amount of water equals to 37 million times of Olympic swimming pool. From the chart, we can see that this was the water usage from 2015 to 2025. It was as expected to increase 20% of the water usage, which means that the need is rising.
So we know all those big numbers about the serious pollution, water scarcity, all of issues. So we decided to dig into the matter and solve it immediately. By doing that, we consulted some experts on the matter and finally decided on settling on using the bioremediation method way to solve all these problems. And also, we would like to know if our project can be implemented in the real world. So this is why we interviewed some clothing companies, such as Xinguang Textiles. And they told us that they actually generate a lot of wastewater during their manufacturing processes. And these wastewater could be recycled. The clothing production costs could actually be lowered, and also the water will be recycled, creating a more environmental friendly environment. Another company we interviewed is the Lab 22 company. And here, the company director actually verified us about our idea. He also mentioned a further collab in the future. So after we finished our interview, consults with the experts and also clothing companies, we decided to make a few adjustments to our project. And finally, it is the birth of our project Decolorgy, meaning decolorize and also decology. To sum up, the advantages of our project actually include our feasibility and our innovative way of solving the problem, and also we can provide a low-cost clothing production for textile companies, also solving the water scarcity issues on the way, and also solving the wastewater pollution along the way.
Now, we know the feasibility of our project, so how we can apply it into our real-life situation. We went into a deeper look into the procedure of dyeing. We noticed that the clothes will be put into the dyeing box, and when the water was used, it will then turn into the wastewater and won't be reused, which we think that this is where we can show off our skills. So how exactly is our project going to work? In the dye box, we will put a piece of PE paper to collect all the colored dyes. On the surface of the PET paper, there comes a complex protein. So the protein will break down the dye molecules, and then the water will turn into clear and we can reuse it. So our experiment was composed of 3 different parts. For the first part is Lycus with NG catcher, which can be removing the color. So how we let the protein stick with the PET paper, here comes our hydrophobing. To let the 2 proteins, hydrophobing and Lycus, to bind together, then we'll introduce our NG catcher and NG tag system with our K-tails. So for the first cycle of the dye removal, we employed 4 different kinds of Lycus. We use his tag purification system to collect the Lycus with NG catcher. We had induced IPTG to express our target protein. To ensure the linkage, we will then introduce our K-tails. the arcade tails will bind with NG catcher to make its linkage more effective. For the second cycle, it's how we connect with the PET paper. Hydrophobing will change its surface, the characteristic of its surface. We will put the PET paper into the dye bath, and the PET paper will then collect all the colored dye so that lacquers can start to functioning, and letting the water become clear so we can reuse them. So how do we prove our concept is working? As for the lacquer's efficiency, we can see it through the ABTS assay. As the sample became more green-blue color, which means that lacquers will start functioning. For hydrophobing, we can test it through the water contact angle test, as the angle is more than 90 degrees, which means that hydrophobing has changed its characteristic of the surface. And to confirm the binding efficiency, we then will use the green fluorescence protein. We can see it through the color changing of the glowing green and notice that the rate of detachment. For the results, we can see from the SDS page. So this is before improvement and this is after improvement. After we change the concentration of elution buffer, we can see that the SDS page is more clear and more specific and easy to tell. That will be the chart regarding to different results of different lacquers. And we can see that the strain of BPUL with NG catcher make the most of it.
So we previously mentioned about our SDS page experiment, so we wanted to verify if our protein can successfully bind together. Well, apart from that, we also did some 3D models just to double check if our proteins can really bind to each other. And here, I will be talking about our model, and it will be divided into 4 major parts. First of all, we put the protein sequences into the AlphaFold software. And so here, we get some simulations on how our proteins would actually look like. And the next part is that we put the simulations from AlphaFold directly into ClusPro, which is a docking software. And here, we can actually see that the tag here and the catcher over there are actually sort of far away, which is quite different from what we first expected, because we thought our tag and catcher actually are supposed to be binding together. And so why would that happen? Well, we thought about some possible reasons. Maybe it's because of there's some modifications of the catcher protein. Its structure just somehow got changed when it binded to other proteins. So tag just cannot fit into catcher. Or maybe it's because of, in this picture, we actually saw hydrophobin binding closely to catcher, then tag binding with catcher. So maybe we thought about it's because of hydrophobin interfering with the tag and catcher binding. So how do we solve these problems and make our proteins bind to each other? Well, we could do some sequence modifications, and also maybe we can change the classes of our hydrophobin. Maybe we can select a different class of hydrophobin, maybe the DUA series, which doesn't produce much infusion proteins, and that could alter the results. Aside from our model, we also did some hardware just to assist our wet lab stuff. Just a quick recap. Here is a proof of concept page we mentioned earlier. We wanted to measure our lactase activity using the ABTS assay. And so we wanted to make a spectral photometer just for the ABTS assay for our wet lab. And here is our spectral photometer. And we actually have 3 special features of our spectral photometer. The first one being affordable. Why is this? Because, well, there's a lot of photos on the internet about the prices of the spectral photometers, and it's actually over 300 or to 1,000 US$, which is actually quite a lot. I mean, because we're students, right? And so, as poor students, we wanted to make some affordable spectral photometers. And here is our chart. we've added the prices of the components of our spectrophotometer. We finally ended with $14, which is actually a very different contrast to the $300 and $1,000. And as for the second feature, being portable, well, you can see here in the background, that black thing is actually a mobile charger. So you can probably assume that our spectrophotometer is actually quite small. So it's easy to take it away and take it anywhere you want. And finally, as for our last feature, our accuracy of the spectrophotometer, we actually swapped some components of the spectrophotometer for some cheaper ones. So it's very, very possible that we wanted to make sure that our spectrophotometer has some decent accuracy. We made some tests about the accuracy of our spectrophotometer. Well, this test is the absorbance of our spectrophotometer, and we're using the copper sulfate concentration here. And as you can see, our R-square here is 0.995, which is actually just above the baseline of 0.995. But we wanted to make it better, so we actually changed a sensor in that spectrophotometer. And here we have another test result, and we actually have a slight improvement over our first version. So I previously mentioned the features of our spectrophotometer, and now you might be wondering, how does this spectrophotometer actually works? In our design, we actually combine our spectrophotometer with our own software, and so they can actually work together. Here's our footage of our team member operating our spectrophotometer. And here you can see there are two buttons, blink and test. So first of all, we press the blink button, and then now we can put the sample we want to test into the cuvette tank, just as the footage shows. And after we finish putting the samples into the cuvette tank, we can now press the test button. And as you can see here, there's going to be one more line of data, like after the number 4, right? And okay, apart from that, we can also press the other button so that we can calculate a trend line for our test results. So we've talked about our project's goals, our project's backgrounds, and how we spend our time in the lab doing a lot of stuff. And so you may be wondering, so do we just stay in our lab and do our works and just do our SDS pages, etc.? Well, not exactly. And here's our education. We've actually done education for a lot of different age groups, ranging from kids, high school students, to college students. For kids, we made them an e-book for them to know about the importance of conserving water and buying less clothes. And as for high school students, we did a workshop on them, and we made a workshop for them, and we shared our experiences in iGEM, and also conducted some interesting experiments for them to let them know what synthetic biology could be like in real life. As for college students, well, we did a lecture for our peers, and we talked about our experience through iGEM, how our struggles and how we stay strong in the end. Also, we did a mobile booth promotion for the school just to let others know about what our project is about in a very simple way. Now moving on, let's wrap everything all up. The perilous intersection between water scarcity and also dye pollution has always been a huge part of environmental problems in Taiwan. And this is what our project Ecology aims to solve. In our journey, we met with so many people. We faced so many hurdles and challenges, and we garnered our resilience, our adaptability, and also we learned that teamwork is the utmost important. And in the end, I would like to say, Ecology saves the world and will make Taiwan the beacon of hope in water tackling issues. Thank you for your listening. We are CSMU Taiwan, logging out. Thank you.